All right, so 5-7. So yesterday we talked about inequalities in one triangle. So you tell me the largest angle based off the largest side, right? You can tell me the smallest side based off the smallest angle, that kind of thing, right? Okay, so you could be able to tell me information about side lengths based off knowing angle measurements, and you tell me information about angle measurements based off of side lengths, right? We do that comparison. Today I want to kind of transition that into talking about it with inequalities for two triangles. The geometry here is not all that difficult, okay? Usually I get a lot of people to be successful in the geometry part of it, but the algebra part is going to be involving solving inequalities, okay? So we struggle a little bit with that because it's something we haven't talked about since maybe the middle of last year. And then there's always one little kind of intricacy that we have to talk about with some of these problems because of distances having to be positive numbers and angles having to be numbers between 0 and 180. So it adds a little bit of extra work that some people kind of forget to do. Okay, so we'll talk about that as we see some examples. But this is called the SAS inequality theorem, and we'll have an SSS inequality theorem here in a little bit. What I want you to understand, and I need you to know, we've already had SSS and SAS, right? But those were for congruency, right? So now, whenever you say SSS, you have to attach to that. Is it inequality or is it congruence? Does that make sense? Okay. When we get back from Christmas and we start talking about, I think eventually chapter 7, we bring in SSS similarity. Okay. So there's going to be kind of categories of these types of statements: congruency, inequality, and similarity. We need to be able to attach that tag word to know which one we're talking about. If I just say SSS or SAS, now I'm being ambiguous because we have more things that could be referencing to. So we need to have that. This is also referred to as the hinge theorem. Okay? A hinge, like the hinge on a door or a cabinet or whatever, is this kind of idea, or the hinge on like scissors or whatever, is being expressed here within this inequality. It says if you have two sides of one triangle congruent to two sides of another triangle, but the angle that is stuck between, the included angle, they are different, okay, they're unequal, then you can go opposite those unequal angles, and you should be able to tell me how those third sides are unequal. Does that make sense? So right here, I know, I'm going to go off of looks here, but let's say this angle here is bigger, and this one here is smaller. Does that make sense? Okay, so we have a side congruent to a side, a second side, but the angles in between those two sides, so it's this angle right here in our name, SAS. That angle is different. We know which one's bigger, we know which one's smaller, right? I should, because of that information, be able to go opposite that angle and say that segment is bigger in comparison to what's opposite that one. That segment is smaller. Does that make sense? Okay. So the way that you compare the angles in SAS is the exact same way that you compare the sides that are opposite. Okay. Now the reason it's called a hinge theorem, if you look back here, we got this piece of paper, right? Okay. Fold it in half, and I open it and close it like a hinge on a door, right? Does that make sense? Okay. Well, right there, you agree that no matter how I open or close this, that's supposed to be purple. That purple line segment and that red line segment are the same length all the time, right? So those are the two S's that are equal. Here, the angle in between is different than the angle in between here, right? Well, if I could imagine it connecting an imaginary line from those two dotted points, okay, those black points, would that line segment be smaller there than it would be there? Yeah, and that's because this angle here is larger, right? The smaller the angle, the closer those two endpoints of that segment, or those two sides, are to one another, so that third segment is small. The larger that angle, the further away those two endpoints are, so then to connect them with the third segment, that's got to be a larger segment. Does that make sense? Okay? So that's every door that you open, every cabinet that you open, whatever, is kind of expressing the hinge theorem. If we talk about scissors, I don't know where my scissors are. Now, same thing can happen. You can see the same thing with scissors. There they are. Okay, so this rivet here, okay, is the hinge, right? Does that make sense? The legs of my scissors, the blades of my scissors, are they always the same length? Okay, so there you've got a side, an angle in the middle, and a side. And then when I change them, I got a side, an angle, and a side. That angle in the middle is now different, smaller. So the distance between the tips of my scissors is smaller, right? When I change that angle, the distance between the tips of my scissors are longer. Okay, so a lot of times you see that kind of picture, that kind of imagery when you look at side angle side theorem. If that didn't make sense, hopefully maybe this will kind of hit home with us. I'm going to, in investigating inequalities, and this is something that you guys are going to do in a lot of your math classes. When you investigate inequalities, the first place to start that investigation is in regards to equality. Because if I know where things are equal, I automatically know that everywhere else they are. Okay? If I know where two things are equal, then everywhere else, every other value that maybe I choose for x or whatever, is where they would be unequal. Okay? So here in this case, I'm going to start with my two angles, alpha and beta here. Alpha being this green one on the left, beta being the purple one on the right. I'm going to start with them being both 45. Okay? You see the blue segments are congruent and the red segments are congruent, right? They're both 2.5 and 3 respectively. So right there we got side angle side, right? But the angle in between is congruent. So we have side angle side congruency here, right? Meaning that those two triangles, if I were to overlap those two triangles, I don't know if I can. Yeah, I've got them kind of positioned off of one another. So if I could drag this one, it's going to land exactly on that one, right? Because they're congruent. And that means that opposite alpha is 2.15 and opposite beta is 2.15. Well, if those angles were congruent, that measurement of 2.15 and that measurement of 2.15 had to be. Let's change this alpha. Let's change it to 50. If I change it to 50, now we have side angle side inequality, right? This angle alpha and that angle beta are different in that relationship. The green one is bigger than the purple one. Okay? Therefore, when I look opposite alpha, 2.37 has to be bigger than the 2.15. Does that make sense? Okay? So if I know where they're equal, if I know the measurements for these angles when the two triangles are congruent, then when I start changing one of those angles, I now have inequalities, and the larger this angle here is, the larger that has to be there. Okay? If everything else is consistent, then we say a 3.73 is going to be bigger than 2.15, and that's obvious, right? I can do the same thing with, I can change both of these or whatever. I can go less than. If I go less than, okay, so now this alpha is 35 degrees, 10 degrees less than the beta. So then you see that opposite that 1.72 needs to be a smaller distance than 2.15. So that's the hinge theorem. And the idea is, if this is, let's see if I can hide that. Show. Can't hide it. I don't know why. We're going to do that. Okay? If I look at just these angles now, okay, so do you agree that that's a side angle side concept? This here is a side angle side concept. So C and B, those would be kind of like those black points that I was showing you on that piece of paper a minute ago, right? So if I want to connect C and B or F and E, the angle across from CB is smaller than the angle across from EF, okay? The distance CB is going to be shorter than the distance EF. Is that all right, Larry? I want to make sure we fully understand that concept, that comparison, before we start doing some examples. Okay? So that's a side angle side inequality. I think it's important that you write down maybe somewhere with side angle side inequality that you are making a conclusion about segment lengths, okay? So we are comparing angle measurements. Oh, wait, sorry, let me rephrase that. We're comparing angle measurements. Said that right? To make a about lengths. Okay? Comparing angle measurements to make a conclusion about lengths. All right, so in your homework questions tonight, when you are seeing expressions that are representing segments, okay, and I got to solve for x, are referencing against segments, I'm probably going to use the side angle side theorem to do that. So I'm going to use angles to help me decide how do I compare those lengths. Does that make sense? Okay. If they're asking me to, if they've got expressions in for angle measurements, and they're asking me to compare angle measurements, this is the theorem that I'm going to use to do that. Okay, and I know these are lengthy theorems. There's no kind of way around that. These are written the most concise way. This is called the side inequality theorem. Okay, so here the argument is that this side here, and it doesn't really matter which one you pick off here. I'm going to pick off the middle one, just because in the last one, the middle object was the one that was unequal, right? The angle was unequal and it was in the middle. So let's say at this one here, we've got three sides, but the middle side is unequal. Okay? So I have two sides that are congruent, and I have a side that is incongruent, or a set of sides that is incongruent. Therefore, I know information about all side lengths, right? So the conclusion can't be about side lengths. I already know everything about them I need. So the conclusion is going to be about angles. And so what this theorem says is that if you start off with two sides of one triangle congruent to two sides of another triangle, but the third sides are different, then the angles opposite those third sides are going to be different in the same exact manner that their sides were different. Okay? So this one we're making a conclusion about angles. This is the converse. If we were to sit down and kind of analyze this the way this was written and identify the if and then and compare that if and then to the hinge theorem's if and then, find out that these two statements are converse to one another. Okay? So the SSS inequality theorem, another way of saying that is maybe it's the converse of the hinge theorem. Okay? I don't know if you ever see it written that way. Maybe some textbooks might, but most frequently in a high school course they use SSS. But it's got to be an inequality. We're going to remember that. We got to put that tag word on there. Picture-wise, all it's saying is if I look at these two triangles up there, triangle with angle A in it and triangle with angle B in it, can you tell me which? So we got two sides, two sides, right? If I look at this dotted line, can you tell me a relationship about the dotted lines to one another, the white one and the red one? Which one's bigger? The white one's bigger. And I know we're just going off of visuals here, but if this one's bigger and this one is smaller, okay, then I'm going to look opposite those segments, opposite to angle A, and look opposite to angle B, and we'll make a comparison about angle A and angle B. Like I said, the comparison of the angles is the exact same comparison you made about the sides that were opposite. Angle A side was bigger, right? So angle A has to be bigger. Okay? So angle A is greater than angle B. And I just make that, in this case, make that inequality symbol kind of ridiculous looking because I think sometimes people get confused like this. It looks like another angle symbol just going the other direction, right? But angle A is greater than angle B. Okay? And that's the comparisons that we're going to make. We're going to try to decide, are we comparing angles to make a conclusion about lengths, or are we comparing lengths to make a conclusion about this? When we think about it, look at the then part. It says something about the angles, right? Okay, it says then the included angle of the first is larger than the included angle of the second. So when we do this one, the SSS inequality theorem is comparing lengths to make an argument about angles. Or I think in the last one I said conclusion instead of argument. Okay, so comparing lengths to make an argument about an angle. So our result inequality that we have to work through algebraically is going to be developed by comparing lengths and then taking the expressions represented by the angles and compare them the same way that the lengths were compared. We'll probably have time. You guys might have time to do all three of them, but we'll do at least two of these problems today. That being stated, if I look at this here, okay, it's the same idea, it's the same concept. I want to start at equality, okay? So right now, these two triangles, I don't know why that arrow is there, but those two triangles are congruent, correct? By side, side, side. Does that make sense? We know information about all three segments. So if I put in that one's distance, and I put in that one's distance. So we are looking at those things, and the comparison that we're trying to make is the CB length to FE's length. And right here, they're the same. So then all three S's are congruent. SSS, we have SSS congruency. Therefore, by CP, CTC, the angles opposite have to be the same, right? The angle opposite CB has to be the same as the angle opposite FE. Well, once I change that, once I make BC get bigger, okay, now I no longer have SSS equality or congruence, right? Now I have SSS inequality, where the third sides, CB and FE, those third sides are different. One's 4.8, one's 2.8, right? 2.8 is bigger than 2.8, correct? So look opposite those opposite those sides and find the angles. Find the green angle, angle A, and find the purple angle, angle D. They need to be in the same relationship that the segments were. So 4.8 is bigger than 2.8, so angle A is bigger than angle D. That make sense? And I just got to auto-fill in the measurements. You see that the green angle is 121.29, and that the purple one is 60.4. Obviously, those are different, right? Okay. And because, I mean, you can even start to see that, 2.8 and 4.8, okay, the lengths of those things, let's say I go to 4 and make this one go to 2, okay. I just want to make sure that people don't make the argument that because this one is twice as big, because that one is twice as big as this one, it does not necessarily mean that that angle there is twice as big as that angle. Does that make sense? Okay. Make sure we're not making that conclusion, and that is not a valid statement. So that is side, side, side inequality. Is that all right, everyone? Yep. Okay. So let's do some examples. Great. All right, so I'll give you a minute to write that one. Did you ask me? Did you say that I didn't ask you how yours was?
Huh?
What'd you say?
He's breathing on my neck, so I asked him how he's breathing on my neck.
Oh, that's creepy.
I don't breathe on my neck.
Do you guys know that I record these weird conversations that you guys have is always on
Are you recording
tape?
right now?
Yeah.
Alex, breathe on my neck.
Well, write that picture down. Alex, stop. All right, so we're looking, and I've got all the information on there. It tells you you're going to compare the angles. So if you're going to compare the angles, that might kind of lead you or provide you a little bit of insight in what they're asking on to what theorem, SSS or SAS, that you're going to use. Okay, I'm going to approach this question as if I don't give you that stuff. So I think the kind of most natural way of doing any one of these problems, depending on, regardless, I guess, of which theorem is actually present here. The first thing I do, obviously, both of them, SSS or SAS, you need sides that are congruent, right? Those sides have to be constant in both. So in any one of these examples you're going to get some congruent sides. So I'm going to look at this one. 12 obviously is congruent to 12, right? So maybe that's that first S in either one of those statements. Okay? Would you agree that SQ is congruent to SQ?
Yep.
So that's the third one. Okay? So now we have to decide to go through with this question, to make an argument about something. I have to decide, do we have SSS here or do we have SAS? Okay? Well, look at all the things that you know. Okay? Do you know the third sides?
Yep. The
sides that we have not talked about. You know those things, right? So you can make a comparison about those things, right? Okay? Remember going back, I said making a comparison about side lengths so that we make a conclusion about angles. Okay? So here we're actually using side, because we know everything about the side lengths of the triangle. We know that 14 is what compared to 15? Okay, so this is a smaller value. Smaller, this is bigger, okay? So then when I work my way back into the angle, that angle, which we're saying is 5x minus 14, right? 5x minus 14 should be what compared to that angle? It should be less than 46. Okay, so that is the inequality that we set up based off of the understanding that that angle of 5x minus 14 needs to be smaller than 46 because 14 is smaller than 15. The angles opposite are in the same relationship, the same unequalness or inequality that the segments were in. We generated inequality. Okay, so this is kind of maybe where we got to talk a little bit about our algebra. Okay, that's a linear inequality, meaning the variable is raised to the first power. When you have linear inequality, the only thing that you do different than normal equations, or solving normal equations, is that when you multiply or divide by a negative number, what do you have to do? You have to flip the direction of the inequality symbol. Okay, that's the number one issue that people come across. It's the number one thing that end of course exam would use or knowingly incorporate into the problem to see if they can catch anybody kind of not paying attention to detail. Okay, so we always got to remember that. Otherwise, you solve these equations the exact same way. Now, that's only for linear inequality. So what I want you to understand is that when you go into Algebra 2, college algebra, and I give you a quadratic inequality, you do not approach that the same way. Okay, there's a different technique. If you haven't learned that, you will learn that. Okay, but we got to solve for x. So just solve like a normal equation. You're going to add 14 to both sides, right? And then what? Divide by 5. So x. I don't know why I changed that symbol. It's going to be less than, right? 5x is less than 60, and then x is less than 12. And now we have values for x. Huh? I didn't divide by negative, though.
Okay.
We'll start over at the beginning. Yeah, 5x minus 14 is less than 46, right? Add 14 to both sides. Gives me 60. Divide both sides by 5. 12. If it was a negative 5, you divide it by negative 5, then you would switch it. Okay? So dividing by a negative or multiplying by a negative is the only time that you have to flip that. Okay? Maybe the next one we do, we'll approach it so we have to apply that. So x is less than 12. Okay? Now the reason we have to write it that way is because that is an infinite number of solutions. You cannot physically write down or list all of those solutions without kind of this visual technique. Does that make sense? Okay? We've designed this approach to allow us to write down an infinite number of things. Because if we didn't have this, we would never be able to write all those answers down, right? We would run out of time in life. Okay? So that's how we do it. Now, what that means then is that 11.9999999, however many nines you want to put on there, is the first value that would work for this. It's the first value that would make that angle 5x minus 14 smaller than 46. Does that make sense? For substitution purposes, let's choose 11. Let's say x is 11. Plug that in up there. What's 5 times 11?
55.
55 minus 14.
41.
41. Is 41 less than 46? Yes, so that works. Try 10. Plug 10 in there. I get 50 minus 14 is 36. Is 36 less than 46? Yeah, okay. Plug in 9. Okay, I get 45 minus 14, right? Okay. Let's say give me 31. Okay. So as I'm plugging in smaller and smaller values of x, that angle is going from what? 41, went to 36, went to 31. Okay. What's that value of that angle doing as I put in smaller and smaller values of x? It's going down, yeah. And because it's linear, it's going down by 5. Now here's my question. Plug in 3. What do you get if you plug in 3? No. You get 1. Is it an angle measurement?
Yes.
Absolutely. Plug in 2 for x.
Well, what has to be greater than a...
You get negative 4, right? Can negative 4 be an angle measurement? No. Okay, so even though the geometry and the algebra that we did with that gave us that as a set of solutions, it also gave us some solutions that are wrong. Okay? So what that did is it took our whole number line, because at the beginning of this, we don't know what x is, right? So at the beginning, when we don't know what x, we make the assumption that it's all real numbers, the entire x-axis, essentially. Okay? Doing that work says, okay, now you can cut off all the numbers to the right of 12, including 12, and discard it. Those are not solutions. These are the only things, x less than 12, those are the only things that may be solutions. But some of those, as you see, when I plug in 3, I get a problem, right? When you plugged in 2, you didn't have, or sorry, 3 you didn't have a problem. 3 gave you a 1 degree. 2 gave you negative 4 degrees, right? Okay? So the issue occurred between values of 2 and 3, right? We want to kind of zoom in on that, narrow in on that value between 2 and 3, and this is the way you do that. If we know that 5x minus 14 is representing an angle, right? That's what that's saying. Angles have to be what kind of numbers for us? Positive. So I'm going to say greater than 0. So then I go 5x is greater than 14. X is greater than 14 fifths. Okay? So that's important. Okay? That has to be met. That criteria has to be met by our solutions as well, so we get positive values for our angles. Now, here's the thing. We can dive into this stuff a whole lot more if I were to start giving you other, okay? The kind of the degree in which, in regards to difficulty, I guess, of these problems can be changed a lot the more information that we know, okay? So let's say I know that angle P was like 70 degrees, okay? Then angle PSQ can only be at most 110, right? Not including 110. So we could maybe incorporate that kind of stuff if we knew more things about the figure. Okay, I'm going to try to avoid a lot of that right now, but this will be incorporated in pretty much every one of these questions that we do. We have to make sure that the x value that we choose is not going to give us a negative angle measurement. So now how do I write my answer? Well, there's a couple ways of doing this. Now, because of Math Excel and the way we write in Math Excel, we need both of these to be occurring at the same time. Okay? So I want these as solutions and these as solutions. Does that make sense? The symbol that we use for that a lot of times is that. I don't know if you've seen that before, maybe Algebra 1. But we call it a betweenness statement. The best way, I guess maybe the most kind of safest fail-proof way of seeing what we need here as a final solution is to graph all your inequalities. So you did a little bit of this last year. You graphed 12 and said, okay, if I've got x is less than 12, we put an open dot at 12, and you shade that way, right? Think about it as a number. If x is coming first, x is less than 12. So you're shading the values that are to the left of 12, that are smaller than 12. Okay? Then I'm going to go find 14/5. 14/5, like I said, is 2.8. Looks like right there. Okay, and this is saying x has to be bigger than 14/5. So it's an open dot going the other way. Okay? And right now, because when we deal with these inequalities, we want distances to be greater than 0 and angle measurements to be greater than 0, we're always going to have open dots. Okay? So the closed dot aspect right now in this application isn't going to be worrisome. Okay? Now here's the thing. Anything that I choose in the red is going to satisfy the SSS theorem. Okay? But it doesn't necessarily satisfy this angle being positive. So if I choose that value right there, maybe it's, let's just say 0. Okay? If it's 0, I get negative 14 for an angle measurement, right? So negative 14 can't happen as an angle measurement. 14 less than 46. Yes. So it satisfies one of those ideas. Well, we need to satisfy both, right? So it can't just be, we can't just pick values off there. If I pick values out of here that are blue, just blue out here, okay? What that's going to do, any value, so let's say 20. If I plug 20 in, does that give me a positive number right there for that angle? But it gives me that angle to be 86 degrees, correct? Is 86 smaller than 46? No. So you see how that number kind of contradicts our SSS theorem. So we want numbers that we choose that are going to satisfy both at the same time. So those numbers occur where there's overlap. Would you agree that if I choose a number like
3.57?
Well, that's in there, but that substitution will be hard. Let's choose like 10. 10 would be maybe right there, right? It's on both of those lines. So if it's on both those rays, you get 36 right there. Is that an okay angle measurement? And it's 36 less than 46. Yes, so it satisfies both those conditions. Okay? So what we want to do is we want to understand that every one of these values in here, of the overlap, okay, all of those values are solutions for x. Okay, so how do we write our answer? This is how we write our answer. We'll put x in the middle. Okay? Would you agree that if I choose this x right, hold on. If I choose that x right there, which side of 14/5 is it on? The right side or the left side? It's on the right. And if it's my number line, values to the right are what of 14/5? Greater than, right? So I'm going to write that. I'm going to write x greater than, I'm going to read this from the middle to the left. X is greater than 14/5. Does that make sense? Okay. Now you're going to see the reason why I wrote it that way when I finish this, because now that x, those x's up there in my graph, what are they compared to 12? They're less than, they're the left of 12, right? So can I say x is also less than 12? So what that means is that these x values, they are to the right of 14/5 and they are to the left of 12. Okay, we can read this several different ways. We can read it as 14/5 is less than x, which is less than 12. Thank you.